We're going to begin talking about two more tests for convergence or divergence of a infinite series. And these are kind of categorized together, the ratio test and the root test, but we're going to first in this discussion talk about the ratio test. Pardon me. And you can see the ratio test stated here. We assume that we have some series, and we can use any index. We've been through this a number of times. I could call this K or N or I. I've just chosen to call it the index N. So this is the sum of terms A sub n from n equal 1 to infinity. It's a series for which none of the terms are zero. None of the terms are zero, okay? And there are three different possibilities. We can determine that the sum of the series or the series converges absolutely, which we'll discuss in a moment, if the limit of the absolute value of the ratio of the n plus first term divided by the nth term, okay, is less than 1. And the series diverges if the limit of the absolute value of the ratio of a sub n plus 1 over a sub n is greater than 1 or infinite. The ratio test is inconclusive. In other words, we have to use a different test if the limit of the ratio of those two, pardon me, if the limit of the absolute value of the ratio or the fraction a sub n plus 1 over a sub n is equal to 1. So if that limit is less than 1, then we have a series that converges absolutely. If that limit is greater than 1 or infinite, then that series diverges. And if the limit is equal to 1, then we can draw no conclusions whatsoever. So let's real quickly just discuss the idea of converges absolutely. We take a general series. That series is said to converge absolutely, or it means converges absolutely if both two things happen. The series itself converges and the series of absolute values of the terms converge. So occasionally we can have a series where some of the terms are positive and some of them are negative. And in that case, that series may converge where the original one does not. In other words, absolutely converges absolutely is a stronger statement than just converges, because the original series converges and the series of absolute values also converges. Now notice about this particular test, and this is a big deal over the tests that we've looked at before. We've looked at an integral test and some comparison tests, didn't we? In both of the comparison tests, we had to come up with a brand new series to compare to. In this test, we're just using adjacent terms of the single series. So we don't need an extra series. It's a pretty easy test to apply, and that's what makes it very useful. And notice, I do want to talk about this inconclusive situation here, and the following two examples really illustrate the idea of inconclusive. And inconclusive means that we really don't know. It doesn't mean it converges. It doesn't mean it diverges. It just means we don't know. So for instance, we know that the series, the harmonic series, that's the series of 1 over n values, which is a p series where p is equal to 1. We know that diverges because it's a p series where p is equal to 1. Now if we apply this test, I'll just go through it real quickly. The n plus first term would be 1 over n plus 1, and the nth term would just be 1 over n. And those are both positive, and so the absolute value is not really adding anything to our issue here. So we're looking at the limit as n goes to infinity. I've failed to write that, of this ratio. Now when we simplify this ratio, when we multiply by the reciprocal of n over of 1 over n, we end up with n over n plus 1. And so we really are taking the limit of n over n plus 1, and we have enough tools to recognize that that value is 1. So here the ratio test, we would end up with a value of 1 on this limit, and so we wouldn't be able to tell whether it converges or diverges. We happen to know it diverges. Now, we also happen to know that the p series where p is equal to 2, which is this series, because p is equal to 2, we know it converges. We've been through that, haven't we? And if we apply this test in this case, a sub n plus 1 would be 1 over n plus 1 squared. And when I square n plus 1, I get this expression. And then, of course, a sub n is 1 over n squared. And so when we multiply by the reciprocal, we invert and multiply, we end up with this expression. And it's not too hard for us to determine here that the limit in this case would also be 1. So, the test would be inconclusive, and we wouldn't know about convergence or divergence. And the real issue I'm trying to make here is that we could have the limit of that ratio be 1, and it might diverge or it might converge. We don't know, so we have to use a different test. And speaking of these, in a situation with these p-series, if we're dealing with any p-series, this limit of this ratio is going to be 1. So this is useless for determining p-series. We have our own test for that, don't we? Our own test for that. Well, let's move on to the next slide here. Now, this has a very important statement before we do this problem. The ratio test is useful many, many times when the series involves factorials or exponentials. And what I mean by exponentials is exponents that have the index in them, the n value or the k value or whatever. That's a good rule of thumb to consider the ratio test when we have fractions, a series where the terms are fractions involving factorials or exponentials. And we'll in fact, this very first one's a good example of that. See, we have an e to the n power, well, that's an exponential, and we have an n factorial, oh, that's a factorial. So we're somewhat familiar, or we should be somewhat familiar in the future. If we see this type of series, this is a good test. The ratio test is a good test to try. So what do we need to do to use the ratio test? Well, we need to calculate the limit of the absolute value of the fraction made by taking the n plus first term and dividing by the nth term. So we've got to do some calculations here, and sometimes this is pretty heavily involved in terms of algebra manipulation. But we need to know a sub n, and of course a sub n is just this term right here, isn't it? And we need to know a sub n plus 1. Well, that would just be the next term. That would be when we're at n plus 1 rather than n. So our exponent on e would be n plus 1, and in our factorial, it would be an n plus 1 factorial. So what we need to do is we need to calculate the limit of the absolute value of that fraction, okay? And so that fraction, well, the a sub n plus 1 is this expression, e to the n plus 1 divided by n plus 1 factorial, over the a sub n term, or the a sub n term, and of course the a sub n term is this e to the n over n factorial. So that's what we're working on. Now the work starts here. We need to, and by the way, in this case, n is positive. We can assume n is positive. We're going to infinity. And so the absolute values are really not applicable here, are they? Everything's positive, so we can eliminate the absolute values. And then when we simplify this fraction, that is when we divide by a fraction, same as multiplying by the reciprocal. And so what I'd say is reciprocate and multiply. So the n factorial ends up in the numerator, and the e to the n ends up in the denominator. Okay. Now, let's I don't know how familiar you are with factorials, so let me kind of assume, at least temporarily, you don't know anything about factorials, and let me remind you of what a factorial is. I mean, for instance, if we said 5 factorial, we would start at 5 and then multiply with a number right below that 4, and then with below that 3, and then below that 2, and below that 1. We stop at 1. So 5 factorial would be 5 times 4 times 3 times 2 times 1. And I think that hopefully you've seen factorial before now. But in general, n factorial means we start at n and then multiply with the integer 1 less than that n, and then multiply with the integer 1 less than that n, and then continue all the way down to 1. We're assuming n is a integer, positive integer. So n plus 1 factorial, we'd start with n plus 1, and then we'd multiply with 1 less than n plus 1, which would just be n. And then we'd multiply with 1 less than that, and then we'd multiply with 1 less than that, all the way down to 1. And so if you notice here, n factorial is the same as n plus 1, and the rest of this business right here is n factorial, isn't it? So n factorial could be written as n plus 1 times n factorial. So if we look at our fraction over here, I'm just kind of relating it to what we've got. We're going to have a fraction where we have n factorial in the numerator and n plus 1 factorial in the denominator. So if we look at this part of the fraction right here, then we can write the denominator, n plus 1 factorial, as n plus 1 times just n factorial, as described right above this. And then you can see that the n factorials will cancel, won't they? We'll have the same factors in the numerator as the denominator, so when we reduce that fraction, it will simply be 1 over n plus 1. Now, also, if we look at this, this is not quite related to the factorials here, but it's related to this limit, it's related to this fraction that we've got here. And we do have an e to the power n plus 1 divided by an e to the n power. And let me just remind you that e to the power n plus 1 is just e to the n times e. And so we have this fraction where the e to the n's can certainly cancel, and leaving us with just e to the first power, can't we? So having put all that together, this part of the fraction simplifies to 1 over n plus 1. And this part of the fraction simplifies to e. And so the entire fraction that we're taking the limit of just simplifies to e over n plus 1. So that makes our limit a little easier for us to deal with. We've simplified this fraction, and the limit of e to the e divided by n plus 1 as n goes to infinity. Remember, e is just a constant. It's 2.7 something. It's the n that's changing, and as n goes to infinity, this denominator goes to infinity, gets unboundedly large. E over a larger and larger unboundedly large number, that limit is 0. So since that limit is 0, then what did we say up here? Whoops, what did we say way back up here? My bad. If the limit is less than 1, and certainly 0 is less than 1, isn't it? Then the series converges. Well, now I've made everything disappear accidentally here. Okay, let's kind of. So now we know that the original series converges because the limit is 0, which is less than 1. So here's our second example of using the ratio test. Determine the convergence or divergence. I'm sorry for my mess right there. The convergence or divergence of the series from n equals 0 to infinity of n squared of the fraction or the term n squared divided by 2 to the power n plus 1 over 3 to the n. Now again, this reeks of exponentials, doesn't it? Because we have an n plus 1 exponent and an n exponent. We don't have any factorials. But the ratio test would be a good choice. Okay, it would be a good choice. And so that's what we're going to try to do. So the very first thing we consider then, how do we use the ratio test? We've got to know a sub n, and we've got to know a sub n plus 1. And then we've got to create a fraction of those two, don't we? So first, let's just remember that the a sub n is actually the term, okay? And a sub n plus 1 is the term where n's are replaced with n plus 1s rather than n's, okay? So in the place of n, we have an n plus 1, so an n plus 1 squared. In the place of this n, we have an n plus 1, and then plus the 1 that's already there, and then in place of the n right here, we have an n plus 1 as well. So when we go about simplifying, the only thing we're really needing to worry about is in this exponent on the 2, that's really an n plus 2 exponent, isn't it? Now, of course, the next issue is that alone isn't really what we're concerned about. We're concerned about the fraction and ultimately the absolute value of the fraction and ultimately the limit of the fraction. So it gets kind of a little bit intense maybe of creating this fraction, but we're going to take a sub n plus 1, which is just right here, okay, and we're going to divide it by a sub n, which is just right here. And that's what we get. Now, we're going to invert and multiply. So the 3 to the n will end up in the numerator with the n plus 1 squared and the 2 to the power n plus 2. So this 3 to the n, when we invert, when we reciprocate, then we're going to have a 3 to the n in the numerator. And of course, this n squared times 2 to the n plus 1 is going, when we reciprocate, it's going to be in the denominator, and we already have this 3 to the n plus 1 in the denominator. So we end up with this n squared and this 2n plus 1 and this 3 to the power n plus 1 all in the denominator. And then we just start simplifying a bit. And notice that the, in the case right here, 2 to the power n plus 2 over 2 to the power n plus 1, well, this exponent is just one more than the one down here, so we'll have a factor of 2 in the numerator. And we can just subtract the exponent n plus 1 from the exponent n plus 2, and we'd get a 1. Now, in the case of 3 to the n over 3 to the n plus 1, the exponent in the denominator is larger, and so we're actually going to have a factor left in the denominator, aren't we? If we did a subtraction of exponents, we'd end up with a -1 exponent, which tells us to go to the denominator, or we can just see that we'll end up with, down here, a 3 to the n times a 3. The 3 to the n's will cancel. But nevertheless, you can look at this, you can pause, and you can decide that this is what it's going to look like after we simplify. Okay, so now that was just so that we knew what to take the limit of. Remember, we take the limit of the absolute value of this fraction. And in this case, I've rewritten this a little bit. I put the 2 and the 3 in front, but outside of that it's the same. And as we had a moment ago, everything's positive, and so we don't really have an issue of needing these absolute values in this case, so we'll remove them. And our, oops, I see that's a little misprint. This denominator is 3 times n squared. It's not 3 to a power n squared. So please forgive me. This is times n squared. The only other thing besides that being wrong is in the next step, I've squared n plus 1. I've just multiplied n plus 1 times n plus 1, and this is what it looks like. Well, I see I've made a mess of things here. I apologize. This is 3 times n squared in the denominator, like we see down here, not 3 to whatever that mess is. In the numerator, after I squared this n plus 1, then I just multiplied the 2 with that. So I got 2n squared plus 4n plus 2 after we multiplied that out. And that's all divided by 3 times n squared. And now we use, and you can do this. This is a simple limit for us to take. We'd multiply numerator and denominator by 1 over n squared, wouldn't we? And by this time of the course, I hope you'd recognize that real quickly, and you could even imagine that this limit is going to be 2/3. I mean, that's what the limit will be, and that we can pretty much tell that, can't we? And so this limit being 2/3, which is less than 1, then we can conclude very comfortably, okay, that the original series, which is this, according to the ratio test, does converge. So we know our original series converges. Now, I probably shouldn't spill the beans so early, but you can see with the title of this third example, we're actually going to show divergence, okay? But we don't know that in advance. And here again, notice we have an exponential, a power that's n, and we also have a factorial. So if I was on a test and I noticed the type of series that I had, and I wanted to know whether it converged or diverged, then the ratio test is the test I would consider doing first. Okay, that's as long as I can consider the divergence test, which is whether the the limit of the terms themselves go to 0, and that's not too easy to tell here either. But anyway, let's move into using the ratio test. And remember, when we're using the ratio test, we need to create the fraction of a to the n plus 1 over a to the n and take the absolute value of that and simplify the fraction and so on and so forth. That's what we're after. So we know a to the n is just n to the power n over n factorial, and a to the n plus 1, now what we'll do, we'll replace every n with an n plus 1. So an n plus 1 to the power n plus 1 divided by n plus 1 factorial. And of course we take the absolute value of the ratio, that is, of the fraction created. Okay, but since a sub n and a sub n plus 1, neither one of them are ever 0, and they're always positive, so we don't need the absolute values, and this is the fraction, what the fraction would look like. Now, of course, the next thing we need to do is to simplify that fraction. So we reciprocate and multiply. The n factorial will be in the numerator, and the n to the n power will be in the denominator. That's pretty intensive here again, but let's notice that n factorial, n plus 1 factorial is n plus 1 times n factorial, we saw previously, didn't we? And so the n factorials will cancel, and we'll be left with just an n plus 1 down here in the denominator. Now, there's not really a whole lot we can do with these powers, but notice this. Here's n plus 1 to a power, and we have an n plus 1 period down here, just the factor n plus 1. Remember, it was n plus 1 factorial, but we simplified these two pieces together. Now, that means we have 1 power of n plus 1 in the denominator and n plus 1 powers in the numerator, and so when we simplify that part, that is, we'll take this exponent 1, subtract from this exponent n plus 1, and we'll just have an exponent of n. Okay, so this part of the fraction right here simplifies to n plus 1 to the n power. So we have n plus 1 to the n power divided by n to the n. Now, with being a little bit clever, and I'm not claiming cleverness for me, but these are things you start to look for. Notice we have a power of n in the numerator and denominator, so we could think of the fraction n plus 1 over n to the power n. In that case, we just apply that power to the numerator and denominator, wouldn't we? So we're going backwards. And then if we look at this next step, we might not think of this, but this fraction, n goes into n, and n goes into 1 over n. So we can break this into n over n plus 1 over n, which simplifies in this form. So what we really have, see, we haven't even taken the limit yet, but this absolute value of this fraction simplifies to the expression that we have right here. So that's what we take the limit of. The limit of the absolute value of a sub n plus 1 over a sub n is the same as the limit of 1 plus 1 over n to the nth power. That's how it's simplified. Now, that's a limit that we've studied about in the past. The limit of 1 plus 1 over n to the n power is equal to e. You know, and when we studied those things first, that's when we were, that may be in Calculus 1, but I think we've reviewed it here in Calculus 2. That's when we had to use L'Hopital's rule in a special way. We had to do some special work with this. But anyway, the limit of that is e. And of course, e, since it's 2.7 something, is bigger than 1. Now, if the limit of that ratio is bigger than 1, then that's the time that we know that the series diverges. So our original series diverges, adds up to infinity, okay? Keeps getting larger and larger and larger. So there's an example of that situation. In our fourth test, again, I've kind of given it away that we're going to use the ratio test, but we're going to get an inconclusive result, which means we won't be able to tell whether it converges or diverges. And if we needed to know, we'd have to resort to a different test. But we need to see what it looks like when we have something that's inconclusive, so we know how to deal with it. or know how to make a conclusion from that test, which is simply inconclusive. Anyway, we're to determine the convergence or divergence of the series that is from n equal 1 to infinity of negative 1 to the power n times the square root of n over n plus 1. So we've seen the idea earlier that when we have negative 1 to the power n, as n goes from 1 to infinity, our terms are alternating in sign. When n is 1, we have a negative 1. So we have a negative result, a negative term. When n is 2, we have a positive 1. So we have a positive term, and so on all the way through. So anyway, we're going to try to use the ratio test. And so using the ratio test, we need to determine a sub n and a sub n plus 1. Well, a sub n is simple. A sub n plus 1, all the n's are replaced with n plus 1s, aren't they? And so we get the term negative 1 to the power n plus 1 times square root of n plus 1 over n plus 2. Remember, you can stop, pause, slow down anytime so as you have a chance to look at this. I'm going to go through this one pretty rapidly because we have some experience already. So next we need to create the absolute value of this fraction. And now here absolute value ends up being a little bit of a deal because we have these negatives in here, okay? So that's the fraction that we'd be looking at. Now what I'm claiming is since we have negative 1 to the power n plus 1 divided by negative 1 to the power n, that is just negative 1. I mean, it would be negative 1 to the power n plus 1 subtract n, which is just 1, isn't it? And it really another way to think of this is n is an even number. Up here we have a odd power. And so we'd have negative 1 over, if n is an even number, a positive 1, and vice versa. So regardless, this fraction is going to give us a negative 1. Now when we reciprocate and multiply, the n plus 1 of this denominator ends up being in the numerator. Okay, so we have an n plus 1 times the square root of n plus 1. And the square root of n ends up being in the denominator, and of course the denominator was an n plus 2 before. So that's how that fraction will simplify. Let's move on up here. So now, because this is all of n is going to infinity, so all of this part is positive. And so when we take the absolute value, basically we're just going to eliminate that negative 1, aren't we? So this is what the absolute value of a sub n plus 1 over a sub n looks like in its simplified form. So that's what we take the limit of. Well, as we take the limit of this, okay, and I've just shown it here as n goes to infinity, this is what we're taking the limit of. Remember way back in Calculus 1, the limit of a product is the product of the limits provided the limits are defined and exist. And so what I've done is I've thought of this fraction as this n plus 1 over n plus 2 times this square root over this square root. And so we're taking the limit of each of those pieces separately. Now, I also thought, well, the square root of n plus 1 over the square root of n is the same as the square root of n plus 1 over n. So that made that look a little simpler. Now, we'll just come on down here. It should not be difficult for us to calculate the limit of n plus 1 over n plus 2. That's a straightforward observation. And in this case, when we look underneath the radical, we should not have any trouble finding the limit of n plus 1 over n, which is 1. And so we have the limit of the square root of 1, which of course would just be 1, wouldn't it? So here we get a result of 1, here we get a result of 1, so 1 times 1 equal 1, and here's the situation where we can draw no conclusions. So we still don't know. You know, when the limit of that ratio is 1, then we don't know whether the regular series converges or diverges, and so we have not really helped ourselves here. At this point, we would have to use a different test. Right now, we're just practicing the ratio test, but if we were going to answer the question, we'd throw up our hands and say, I've got to find another test so I can make some decisions. Well, this next one is the last example I want to look at. And quite frankly, here, I know you can deal with this test. What I'm trying to do is to remind you of techniques in limits, because we have to rely on things we've learned previous to this to be able to do these parts. So here we're asked to determine the convergence or divergence of this series, which is also another alternating series, basically. Alternating meaning the terms alternate from positive to negative, and that's created because of this -1 to the n power in the as part of the term. So we're going to use the ratio test again, as we've thought. And in this case, now here we don't really have exponentials or factorials, so we might determine ahead of time this might not be the best test to use, but we're going to try anyway. So we create the limit of the absolute value of a sub n plus 1 over a sub n. And we're faced with the same kind of thing that we had a moment ago. This -1 to the power n plus 1 over -1 to the power n is just a -1. And when we take the absolute value, then we're not worried about that -1 any longer. And so I removed the absolute values here because of that piece. Now, when we look at this fraction over this fraction, we reciprocate and multiply, and this is what we get. Now, as in the last problem, then I'm looking at this as the limit of n over n plus 1 times the limit of natural log of n plus 1 over natural log of n. And we can think of that fraction as a product. And so if we have the limit of a product, that's the product of the limits, which is what I've shown here. Now, in this first limit, this is straightforward. We could say multiply by 1 over n in the numerator and 1 over n in the denominator, and we'd have the limit of 1 over 1 plus 1 over n. And of course, that's going to go to 1. So the limit in this first case is 1. Now, in this second case, if we look at the log of natural log of n plus 1 and the log of the natural log of n, as n goes to infinity, this natural log goes to infinity, and so does this. So this is of the indeterminate form, infinity over infinity, which is when L'Hopital's rule applies. And remember, this little h means I'm applying L'Hopital's rule. So I'm going to convert this to the limit of the derivative of the numerator divided by the derivative of the denominator. And the derivative of natural log n plus 1 with respect to n is just 1 over n plus 1, and likewise the derivative down here is 1 over n. So now I have a new limit to consider, and if I reciprocate this, 1 times that, so I don't need the 1 times any longer. When I reciprocate, I'll get n over n plus 1, and the limit of n over n plus 1 as n goes to infinity, just as we saw above, ends up being the same as, that's just a 1. So here is a second example of where the test is inconclusive. And we don't know still whether this converges or diverges because the ratio test didn't help us. Now let's back up one step here and notice in these two examples, and I don't mean that this would never work, but in these two examples where it was inconclusive, we didn't have exponentials or factorials, did we? In the examples that we saw before where it helped, divergent, we found out here we had exponentials and factorials. In the example before that, we had exponentials, and we drew a conclusion. In the example before that, we had exponentials and factorials. So don't rule out using the ratio test, but you've seen in these 5 examples where it was useful and where it was not, and maybe that's a good information for us to consider in the future. Well, next we'll talk about the root test, which is also simple to use, but that's for another discussion.